All right, so my name is Stephen McGee. I'm with the Learning Partnership, and our group was the outside evaluator for this program. And whereas you saw from Laura's talk that she really delved into the details of the developmental progression of the concepts, what we're going to do in this paper is sort of take a higher level view and focus basically on levels of mastery and how that developed over the course of the curriculum. So we're going to ignore all the details of how the individual concepts were developed. And the title of this talk is really focusing on how the focus on modeling and explanation within the curriculum, how that impacted student learning. Not really going to talk about it in the presentation, but also the impact on identity or identification with the scientific enterprise. And what we found is that students in general achieve large increases on the performance assessments over the course of the curriculum. And it turns out that the extent to which the students actually engaged in inquiry, and we'll get more into that, actually influenced the rate at which they learned. And then from the identity point of view, we also found that the extent to which students identified with the scientific enterprise, which in our case we used expectancy value as the indicator of that, was indirectly influenced also by the extent to which the students engaged in inquiry. And the details for that is actually in the paper. So the data for this comes from a field test that we did in 2 locations in the fall of 2015. We had 5 teachers in Los Angeles who this was the first time that they were using the curriculum. They were introduced to it through professional development in the summer, and then they implemented it in the fall semester. 6 teachers in Michigan who mostly were returning teachers that the team had worked with over 1 or more years. In LA, it was mostly sophomores and juniors that participated. In Michigan, it was mostly freshmen and sophomores that participated. And as you may well imagine, in LA, it was primarily a group of Hispanic serving schools. In Michigan, it was a little bit of a mixture of suburban, primarily Caucasian schools, and some urban, primarily African-American schools. And as Laura went into great detail, this sort of outlines the content that we're going to focus on in this particular presentation. One, dealing with types of interactions, specifically around attraction and repulsion of electrical interactions, as well as the nature of matter. And the practices that were embedded within the tasks were mostly centered around modeling and explanation, and the cross-cutting concept was mostly patterns. So I'm going to walk through the 4 example tasks that we're going to focus on specifically in Unit 1, just to give you a little bit of a flavor of the way the tasks were structured and how they align to the 3 dimensions. So one of the tasks early on in the curriculum, or that represents content from early in the curriculum, has to do with students being given a chart showing data about the repulsion and attraction between 2 different balloons, and they're supposed to generate an explanation as to what the charge is on each of those 2 balloons. A second task is where we actually show them a video in the system with the Van de Graaff where the hair sticks up once you add an electrical charge. So they're asked to develop a series of models of the different steps in inducing the charge and then having the hair stick up to show those interactions. I do make a note that this particular task also includes expectations about Unit 2 understanding having to do with forces and energy. So there's actually 2 different sets of concepts embedded in this task. A third item, also once again showing a video of a rod passing over some paper, doesn't attract, you rub it with some fur, and then all of a sudden now the paper gets attracted to it. And once again, they have to draw a series of models to sort of explain what's happening at each of those steps. And then the 4th one that we're going to focus on is also the one that Laura talked about in her paper, showing the setup of the Rutherford experiment, and students have to develop models to explain the data. So as I mentioned, we're sort of in the analyses that we did, we sort of ignore all the details of how the students develop their understanding, and we focused on sort of the extent to which they mastered that particular task. So we used a Roche framework to scale the items, and this chart shows the different levels of difficulty for those 4 tasks that I showed you. But just for point of reference, we also included the level of difficulty of the tasks that focused on Unit 2 content. And what's nice about this chart, it sort of shows that the order of the curriculum is sort of lined up with the order of complexity of the concepts as embedded in these particular tasks. And you can see from the WIG task, I've broken it out to show the Unit 1 concepts and the Unit 2 concepts. And what the range of difficulty represents is that within a task, there were subcomponents that were scored separately. And so this just shows the range of difficulty of all those subcomponents for that overall task. Okay, so during the field test, we also wanted to get a sense of, somewhat of a measure of fidelity of implementation. But given 11 classrooms, and of course we started with more than 11 and a few dropped out, we didn't really have the capability to go do systematic classroom observations of every classroom. So what we did is we borrowed or adapted a measure out of the University of Chicago from this larger reform measure called the 5 Essentials. They have a scale within that they call the inquiry-based instruction scale. We adapted it to ask after 7 specific lessons throughout the curriculum, and basically said in the last week, how often did you these 5 different tasks. The other way that we modified is the first 2 on that list, we specifically zeroed in on the practices of modeling and explanation. The other ones basically are from their measure, which gets at sort of broader aspects of teaching in a science classroom that we think are important that go beyond the practices themselves. Class discussion, writing, hands-on activities, etc. The other thing why we use this measure of student ratings of teaching is that there's other research that shows that actually that's a useful measure. So one, this particular, the original measure actually is predictive of ACT test performance at the high school level. We also draw from the Gates-funded measurement of effective teaching that have shown that measures of student ratings are actually highly correlated with actual measures of teacher observations from trained raters. So we felt that this would be a valid way for us to get indicators of the variability in implementation of the practices we thought were important. And then just to give you a sense of the scale, so a 3 is where the students said that they engaged in that specific practice a couple of times per week. A 4 is where they said that they engaged in almost every day. So you're getting a sense that these practices in general were a couple of times a week to almost every day that they engaged in. And it was nice to see in terms of the framework that the key practices were actually most relevant, approaching the almost every day they were engaging in at least what they perceived to be modeling and explanation. And then in terms of the data analysis framework, what we ended up with where we had test occasions, we had a pre-test, we had an assessment at the midpoint of Unit 1, an assessment at the end of Unit 1, and another assessment at the end of Unit 2. So we had test occasions embedded within students and students embedded within teachers. So that suggests using an HLM framework for analyzing this particular data. And what we found was that the student growth and assessment across those 4 occasions actually interacted with the scores on that Science Inquiry Index. And it was a linear interaction. And of course, for those of you that have done HLM, to try to understand sort of linear interactions is always very complicated. So what I'm going to do here is actually walk you through a series of graphs that try to illustrate what this relationship looks like. And for the purposes of illustration, I'm actually taking the linear relationship and making it dichotomous, just to help us understand what's going on. So what we have here is a graph, and I zeroed in on just the 5 teachers from the LA context. One of the reasons to focus on the LA teachers is Angie's actually going to talk in more detail about case studies with these particular teachers. But this is just the raw graphing of the Rosh scores for at each time point. And as you can tell, it's pretty messy. Things are bouncing all around. Another thing to notice is that over the course of the semester, the 5 teachers ended up in different places. So we have one teacher who only made it through the first part of Unit 1 in an entire semester. Other teachers made it all the way through Unit 2 during that time period. And of course, who knows what the heck's going on with that dip at the end of Unit 1. Maybe they administered the test right after homecoming and the kids didn't do very well. So the nice thing about HLM is what it does is it takes all the information that we have and parcels out what is our best estimate of growth for a specific student, and then parcels out and separates out the error in that involved in that measurement. So it allows us to sort of zero in and look at the growth, the best estimate of growth for each student, which then I averaged for each student up to the teacher level. So what we're seeing here, and I forgot to mention the previous slide, the green teachers are the ones that were sort of high on that inquiry index. The yellow ones here were the ones what I would call medium. I wouldn't call them low on the inquiry index. And then lastly, what we would do is then average across those that were high and those that were medium. And in this graph, I actually incorporated all the teachers together now. And you can see from this graph the differences in growth rates now between those who had their students engage in more of those inquiry practices versus those that a little bit less so. The effect size for the high group was 1.3 from beginning to end of Unit 1, and the effect size for those that were medium from beginning to end was 0.9. So it's a 0.4 effect size difference between those two groups. So the next question was, well, how meaningful is that particular difference between those two groups? So now if we go back and overlay the item difficulties from Unit 1 onto these growth rates, what we see is actually the difficulty of the Unit 1 items actually sort of in that 5 to 6.5 spread, which is pretty much the difference between those two groups. So what we're seeing is that those who are on the medium level are approaching mastery of sort of the most basic item in Unit 1, whereas in the high group, they're actually approaching mastery of sort of the most complicated idea within Unit 1. And of course, Laura's talk actually has all the white space under here as to what's going on, but we focused on sort of achieving mastery. And then we'll actually hear from Kristen a little bit more detail about the development that went on with that structure of atom work as well. So in the end, I think what we found is that the curriculum and profession development successfully scaffolded teachers to engage students in scientific inquiry. And those that were more closely aligned with our implementation model achieved higher student learning outcomes, as well as achieved higher student identification with the scientific enterprise.